Hello grade 11 and welcome back to another video with me, Miss Martins. If you haven't subscribed to my channel yet, please make sure to subscribe. I do physical sciences videos, I do maths videos, I do a whole lot of videos to make schooling and all those sorts of things easier for you. If this is a video that you've been waiting for, that you want to see, please give it a thumbs up. Let me know in the comments what else you want to see. But today we're going to be going through atomic combinations, which is one of the first parts of chemistry in grade 11. And as you can see over here on my left, I've listed all the topics that we're going to be covering in this video, but we will be looking at it in terms of approaching exam questions. So I'll be going through exam questions with you. They will be dealing with all of these topics over here. If you want to see more videos, I will link more in the description below, and also let me know in the comments if I've missed anything. Let's just jump right into the exam questions. So here's my first exam question. I'm going to be going through each of them relatively slowly. The definitions are flash on the screen, and I just want to make a quick statement about definitions quickly. Definitions are your easy marks in your physics and your chemistry exam. And I know there's nothing easy about memorizing definitions, but you do need to understand that there will always be definitions in your science exams, and you do have to study them. You do have to learn a lot of them word for word. There's important key phrases and key words that if you don't say them in the definition, you will get marked down. There's my definition for covalent bond, and now just please take notes. It is very important to state that a covalent bond is the sharing of electrons, and this takes place between two atoms, and it's to form a molecule. If you just say that it's a bond between two atoms to form a molecule, you won't get your marks, because the main point about a covalent bond is that it involves the sharing of electrons. And if you just say it's the sharing of electrons, you're also not going to get all your marks, because the sharing of electrons between what? So you need to be specific, you need to explain in detail or define in detail. My next question wants us to draw Lewis structures, and our first one is for chloromethane. The name of this compound is called chloromethane, so 2.2.1. Now, the first thing that I want you guys to take note of for this compound is we've got CH3, Cl. Now, if you take a look, we have a carbon atom, we have 3 hydrogen atoms, and we have a chlorine. So there's more than 2 atoms in this compound. Now, when we have a compound like this, and we know that we're going to be doing a covalent bond, there's going to be covalent bonds involved. You can work with your difference in electronegativities to confirm that, but they just asked us to define covalent bonding. So this is a covalently bonded molecule. These atoms are bonded covalently. Now, when we do that, we're going to draw Lewis dot diagrams where they share their valence electrons. Now, because there's 3 different types of atoms, one of them has to be in the middle. Now, this is where students often go wrong. They want to sometimes put the hydrogen in the middle, or maybe the chlorine in the middle. Now, one rule that you can use, it is more of a guideline than a hard, fast rule, because there are exceptions. And that guideline is that generally the least electronegative atom goes in the middle, but this guideline excludes hydrogen. Now remember, electronegativity is the tendency of an atom in a molecule to attract, so to pull the bonding electrons closer to itself. And on our periodic table, it even says here in the little key that the electronegativity is the sideways number. So we know that we have a carbon in that molecule. The electronegativity is 2.5. We have 3 hydrogens with the electronegativity of 2.1. And then we have chlorine with an electronegativity of 3. Now the guideline says that the least electronegative atom goes in the middle, but we exclude hydrogen from that. So hydrogen we're not going to look at. So if we look at carbon and chlorine, the least electronegative is carbon. It has an electronegativity of 2.5. That means that carbon is probably going to go in the middle of that molecule, and the carbon is going to be surrounded by the 3 hydrogens and the 1 chlorine. And this makes sense as well based on the number of valence electrons that these atoms are willing to share. Now remember, when we're drawing Lewis dot diagrams, if you need a recap on this, then I would go and check out my video on Lewis dot diagrams for covalent bonding. I'll link it above and in the description. But when we draw Lewis diagrams, we need to look at the number of valence electrons for each atom. And the shortcut for doing that is if you look at your periodic table, this is exactly the one that you'll get in your exam, or something very, very, very similar. Then the valence electrons are represented by the Roman group numerals. So hydrogen has 1 valence electron. Carbon has 4 valence electrons. Okay, 4 valence electrons. And chlorine has 7 valence electrons. When they share electrons, it's the valence electrons that are shared. Now, as I said, it makes sense that the carbon goes in the middle. And the reason for that is because, as we said, carbon has 4 valence electrons. So 1, 2, 3, 4. We mentioned that hydrogen each has 1. So hydrogen has 1 valence electron. It needs 1 more to become stable. Hydrogen and helium each need 2 in total to become stable. Helium does have 2 electrons, okay, in its first energy level. Hydrogen has 1. That's why it has 1 valence electron. It needs 1 more to reach a full outer energy level structure. So each hydrogen has 1. And if you look at what that means, it means that the hydrogen shares that 1 electron with the carbon, and the carbon shares 1 electron each with the 3 hydrogens. So now each hydrogen has 1, 2, 1, 2, 1, 2, so they're full, they're stable. And chlorine, we said, has 7 valence electrons. So now I'm going to use crosses to represent that. It's 1, 2, 3, 4, 5, 6, 7. Chlorine needs 1 more valence electron to reach the octet structure. Octet means 8. If chlorine has 8, it is then full, it is stable, it has a full outer energy level, and it reaches that octet structure because of this 1 over here that it shares with the carbon. And if you look at the carbon in the middle, if you count all the little dots and crosses surrounding the carbon also has 8. And that's how you do the Lewis dot diagram. So I'm going to do it a little bit bigger here for you once more, just so that you can see how it is done. So we've got carbon in the middle. Carbon has 4 valence electrons. 1, 2, 3, 4. We know carbon goes in the middle because it's the least electronegative. It's going to be surrounded by the 3 hydrogens, each of which has 1 valence electron. 1 valence electron and 1 valence electron. But immediately we can see that each hydrogen is now full and stable because each of them now have 2. Then the chlorine, which has 7, also going to represent those 7 with X's. 1, 2, 3, 4. Start here again. 5, 6, 7. The chlorine is also full and stable because that dot over here, the valence electron from the carbon, is now shared with the chlorine, giving it an octet structure. So if I have to draw the Cooper structure for this, we've got a single bond over there, a single bond over there, single bond over there, and a single bond over there. Okay, there we go. And that's the structural formula for chloromethane. Remember, if they share 1 pair of electrons, it forms a single bond. Okay, carbon dioxide is slightly more complicated. So we've got carbon, we've got oxygen. We know the carbon's going to go in the middle because there's 2 oxygens. Each carbon has 1, 2, 3, 4 valence electrons. And each oxygen, I'm going to redraw the final one for you now, but I just want to show you. Each oxygen has 6. 1, 2, 3, 4, 5, 6. This one has 1, 2, 3, 4, 5, 6. Remember what we said? They need to reach octet structure, which means they need 8 electrons. Each oxygen only has 6, which means it needs to share 2 more. So these 2 over here are going to be shared with this oxygen. Okay, these 2 little lone ones over here are going to come to the middle. These 2 X's are going to come to the middle. We're going to see what's going to happen there. And then on the other side, the same thing is going to happen. We're going to have these 2 over here, which are currently alone. Can you see? They're just little dots alone. Those 2 have each other. Those 2 have each other. These 2 are all alone. They're going to share with the carbon over here and these 2. So how my final diagram is going to look, and the only one that you need to draw for me for marks, will look as follows. My carbon in the middle, and remember we said that those 2 crosses, those 2 electrons, are going to be shared with the oxygen that's right next to it. Those 2 yellow dots are going to be shared. So we're going to see what's going to happen. All the other dots on the oxygen we draw in as normal. Now, I just want you to double check. This oxygen has 1, 2, 3, 4, 5, 6, 7, 8. I'm including the crosses in my counting because it's sharing those crosses with the carbon. And the same thing on this side. 1, 2, 3, 4. Join the oxygen. 5, 6, 7, 8. So each oxygen has reached octet structure, and the carbon in the middle has 1, 2, 3, 4, 5, 6, 7, 8. Done. Now we can see there's a shared pair of electrons, there's a shared pair of electrons. So that is why we have a double bond over there. Same thing here, shared pair of electrons, shared pair of electrons. We got a double bond over there. Okay, so carbon, oxygen, double bond, carbon, oxygen, double bond. 2.3 says how many lone pair electrons are on the central atom in the carbon dioxide molecule. Now you need to understand that the central atom is the carbon. Carbon's in the middle. Are there any lone pairs on the carbon? No, there's only bonding pairs. Okay, the double bond over there, those are two bonding pairs, those are two bonding pairs. So the carbon has no lone pairs. So we'll say 0, or we'll say none, or nothing, or something along those lines. 2.4 wants us to identify one substance in reaction to, that's this reaction over here, that can form a dative covalent bond when reacting with an acid. Now you need to know the definition of a dative covalent bond. A dative covalent bond will form when one of my substances has a lone pair of electrons on the central atom, okay? And one atom or ion needs to have an empty valence shell. So now, very simple, they don't want us to show it with Lewis dot diagrams or anything, but we should know, or you should know, that water, H2O or water, has a lone pair of electrons on the central atom. If I have to draw the Lewis dot diagram for water quickly for you, you should know that it looks like this. Something like that. Okay, oxygen has 6 valence electrons, 1, 2, 3, 4, 5, 6 with the crosses, and then hydrogen each has 1. As you can see here, we have a lone pair. We actually have 2 lone pairs of electrons on the central atom. Because of that, because we have a lone pair, and if I have to pair that with something that has an empty valence shell, such as the H plus ion, H plus means that it has lost an electron, and you should know that hydrogen atom only has 1 electron. So if it becomes H plus, it means it has lost that electron. So it has no electrons. It has a completely open and empty valence shell. So both of these electrons in the lone pair will be shared with that H plus ion. So basically our water is H2O. Just read the question carefully, because sometimes they can say, give the name of one of the substances. Then you'd have to say water. Or they could say, give the chemical formula of one of the substances, then you have to say H2O. Over here, they just say identify. So I can say H2O, I can say water, it doesn't matter. Our next question asks us to write down the shape of the H2O molecule and the CO2 molecule. So as you can see, the H2O molecule has 2 lone pairs on the central atom, and you need to learn that if an atom has 2 bonding pairs, so there's a bonding pair and there's a bonding pair, and it has 2 lone pairs, the shape is called bent, or you can refer to it as angular. The general formula for this sort of a shape is AX2 E2. They didn't ask for that. They didn't ask for the formula, but I'm just showing you. So A represents the central atom. X2 tells me that there's 2 bonding pairs over there, and E represents lone pairs. We got 2 lone pairs. So that's bent or angular. And the CO2 molecule, you should know, is a linear molecule. There's no lone pairs on the central atom. Linear. Now this question actually comes from a different past paper, but for me it's sort of followed on the previous question, which is why I put it over here. And it says, is the CO2 molecule polar or non-polar? Explain fully. It's only 2 marks, but they want you to explain fully. Now first of all, we identified that the CO2 molecule has a linear shape. And that tells us that the molecule is symmetrical with an even charge distribution. Another way that you can say this is you can say that there's no net dipole moments, or you can say that both ends of the CO2 molecule have the same polarity, and because of this, it is a non-polar molecule. So just remember that if we have a symmetrical molecule with an even charge distribution, and symmetry or symmetrical molecule often happens when we have no lone pairs, just by the way. No lone pairs. So if we have something that is linear or maybe tetrahedral or maybe octahedral or trigonal planar, they have no lone pairs, they have a symmetrical or even charge distribution. There's no net dipole moment, therefore those molecules are non-polar molecules, even though they have polar bonds. Remember, you can have polar bonds, but it doesn't mean you're a polar molecule. To decide if a molecule is polar or non-polar, we have to look at the symmetry, we have to look at the charge distribution. 2.6 says, although molecules of CH4, this is methane, and CH3Cl, this is chloromethane, have the same shape, and by the way, that shape is tetrahedral, I'll show you now. CH4 is non-polar, while CH3Cl is polar, and they want us to give a reason. It's only 1 mark, but I'm going to explain it properly. So as you can see, both of these molecules will have the formula AX4. They're both tetrahedral in shape. However, so it says they have the same shape, but this one is a polar molecule and methane over here is non-polar, and they want a reason for the answer. So basically the explanation for that is that this molecule over here, methane, CH4, this has a symmetrical charge distribution. The molecule symmetrical charge distribution, and it's because of the difference in electronegativities here between CH, 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 CH. So the little dipole moments in this molecule cancel out. There's no net dipole moment. Okay, so basically the charge distribution is even symmetrical molecule. Okay, if you look at this molecule over here, we have a difference in electronegativity here between the carbon and the hydrogen, which is the same on the top, left, and right-hand side. But here at the bottom, there is a difference in electronegativity between the carbon and the chlorine. And because of that, because chlorine has a much bigger electronegativity than the hydrogen, so this difference in electronegativity will be greater, there is an uneven charge distribution in this molecule. It's an asymmetrical charge distribution. And because of that, this molecule is polar. So the one side of the molecule, this top side of the molecule, if you want to say it like that. Remember, these molecules exist in 3D, so just keep that in mind. But this side of the molecule will have a different charge to this side over here because Cl has a very high electronegativity compared to hydrogen. So your answer is that, and just remember that when we speak about symmetrical versus asymmetrical, we're speaking about charge symmetry. Okay, so symmetrical in terms of the charge distribution being symmetrical, even charge distribution, asymmetrical meaning uneven charge distribution, and asymmetrical charge distribution. So that's what we mean when we speak about symmetry. Let's take a look at the next question. So it says electronegativity of atoms may be used to explain the polarity of bonds. So you should know that we have been doing that. If we calculate the difference in electronegativity between two atoms and the difference is 0, it means immediately that your bond is non-polar. If you don't get 0, however, if you get greater than 0, less than 2.1, you know that you're dealing with a covalent bond. Okay, so first of all, define the term electronegativity. Now, just remember what I said about definitions. They are very, very, very important, and there's the definition of electronegativity. So it is the tendency of an atom in a molecule to attract bonding electrons closer to itself. So if you have a higher electronegativity, it means that when bonded covalently, you pull those bonding electrons closer to yourself. So you have a greater electronegativity. That means that within a covalently bonded molecule, the atoms that have a greater electronegativity, that side of the molecule will be more negative. I hope that makes sense. Unless there's an asymmetrical charge distribution, and therefore the charge balances itself out. Okay. Then we have a non-polar molecule. Draw the Lewis diagram of an oxygen difluoride molecule. Now, just by giving us the name oxygen difluoride, di means 2. So oxygen difluoride, 2 fluorine atoms. That's what I'm trying to draw. So as I've mentioned before, we know oxygen has 6 valence electrons, which means it needs 2 more to reach octet structure. Each fluorine will have 2 of them. Will have 7 valence electrons, each of them needing 1 more to reach octet structure. So I'm just going to draw our final diagram over here. We've got 1, 2, 3, 4. Okay, now I'm not done. I know 1 fluorine could go here, 1 could go over here. Okay, just keep that in mind. So 4, we've got 4. We need 2 more. 5, 6. The reason I'm putting those over there is because I know that the fluorine, one fluorine is going to fit in over here, the other one's going to fit in over here, and those fluorines are going to share one of the electrons with the oxygen. And remember, fluorine each has 7, so the dots are going to represent the valence electrons around the fluorine. 1, 2, 3, 4, 5, 6, 7, just like that. Okay, and that cross over there that belongs to the oxygen is now also being shared with the fluorine. So fluorine has reached octet structure, and let's just do the same for the other side. Remember, fluorine has 7 valence electrons. It needs one more to reach octet structure. It gets that octet structure by sharing one of oxygen's valence electrons. And now look at oxygen. It also has 7 valence electrons. There we go. That is it. So as you can see, and I'm sure they're going to ask about this in the next question, but in one of the questions to come, we can see that this is a bonding pair of electrons. That's a single bond. This is a bonding pair. Oxygen has 2 lone pairs on the central atom. So I hope you can remember from earlier, we can tell that the shape of this molecule will be bent or angular, just like water, because there's 2 lone pairs on the central atom and 2 bonding pairs over there. 2.3 says calculate the difference between oxygen and fluorine in oxygen difluoride to predict the polarity of the bond. So to calculate difference in electronegativity, we're going to use the periodic table to find the electronegativity of oxygen and fluorine. So there we go. Oxygen 3.5, fluorine 4. So it is going to be 4 minus 3.5. And my students often ask me, ma'am, must we double any of them? Because I know that I have OF2. So must I double any of them? And the answer is absolutely not, because remember, you're working out the difference in electronegativity for the oxygen and the fluorine within the molecule. So I know there's 2 fluorines, but remember what we're working out is we have a fluorine there and we have a fluorine there. Actually, in reality, I showed you that the molecule is going to be bent. So let's just draw it how it will look in reality. And we have a lone pair there and we have a lone pair there. That's not really relevant to this, but we are working out the polarity of this bond, okay, between oxygen and fluorine, which will be the same as the polarity for this bond. Okay, so we're working out between a oxygen and a fluorine. So it's 0.5. So the polarity of the bond, it'll be a polar covalent bond. Remember, if the difference in electronegativity is 0, then it'll be a non-polar covalent bond. If it's greater than 2.1, it'll be an ionic bond, but this is a polar covalent bond. 2.4 is worth 4 marks, so we know we're going to be doing a bit of writing, and I always tell my students that if you want to get all the marks, you must write and include all the points. They often say to me, ma'am, can we shorten it? Can we leave this out? Do I have to say this? And the answer is pretty straightforward. If you want the 4 marks, you have to write. You have to do the work. Okay, so it says a polar bond does not always lead to a polar molecule, as I mentioned earlier. They want us to explain the statement, and now look what they say. They say by referring to oxygen difluoride and carbon dioxide molecules. In your explanation, they're telling me what to say in my answer. Include the polarity of the bonds and the shape of the molecules. So they're telling you exactly what they want you to say in the answer. Now, just before I write out the answer for you, we know that the oxygen and fluorine bond is polar. We also know that the carbon and the oxygen bond is polar. We worked that out, okay? So polar bonds, polar bonds. However, we drew the Lewis dot diagram of this, and earlier I mentioned that there's a lone pair, there's 2 lone pairs on the oxygen. This molecule is bent or angular, which means it has an asymmetrical or an uneven charge distribution. Carbon dioxide is a linear molecule with an even or asymmetrical charge distribution. So, because oxygen difluoride is asymmetrical and it has an uneven charge distribution, this will be a polar molecule. Because carbon dioxide is a linear molecule, symmetrical or even charge distribution, it will be a non-polar molecule. That is what they want you to say in your answer. Now, this is just to kind of recap before I write out the answer properly. As you can see, oxygen difluoride and carbon dioxide both have polar bonds. And I wrote there the reason why is because of their difference in electronegativity, and I just stated them for both. So they do want me to mention polarity of bonds. Then they wanted me to mention shape of molecules, and remember the shape is always related to the charge distribution. So because oxygen difluoride is bent or angular because it has lone pairs, it has an asymmetrical charge distribution. So just think lone pairs, bent, angular, asymmetrical charge distribution. Then we got our CO2, which has a linear shape with a symmetrical charge distribution. Because oxygen difluoride has asymmetrical charge distribution, it's polar, and because CO2 is symmetrical charge distribution, it's a non-polar molecule. And that's how we're going to lay out our answer, but I'm going to do it in bullet point form. This is just to help you. You can include this in your book as a little summary. It's always nice to look at it like this, and this explains why even though you may have polar bonds like CO2, you're not necessarily a polar molecule. So there's the answer written out for you to give you your 4 marks. Our next question says H3O+, this is called the hydronium ion, is formed when H2O, water, forms a dative covalent bond with an H+ ion. Draw the Lewis diagram for H3O+. Okay, so they tell me that it forms when we have H2O, and we already know that the Lewis dot diagram for H2O looks like this. We know that oxygen has 6 valence electrons, hydrogen each has 1. Then, because we have a lone pair of electrons on the central atom, we actually have 2. One of these lone pairs is going to essentially be shared with the empty H+ ion. Now I'm saying empty because H+ has an empty valence shell. H+ means it has lost an electron. Hydrogen only has 1 electron. We know the Aufbau diagram for hydrogen looks like this. 1 lonely little electron in energy level 1 in our s orbital. So if I have an H+ ion, remember a cation, a plus ion forms when we lose that electron. So an H+ ion has an empty valence shell. It's empty. It needs 2 in order to be full. So both of those electrons here, both of those electrons in the lone pair are shared with the hydrogen, and overall that gives this a positive charge. Okay, so that is how the Lewis dot diagram will look. Some people include this arrow, some do not, but it's nice to show that both of those electrons are shared with that hydrogen. Okay, that hydrogen ion. State 2 conditions for the formation of such a bond. Well, I've mentioned both of them already. One atom or ion must have an empty valence shell or orbital, and as we mentioned in this case, that's the H+ ion, and the other atom must have a lone pair of electrons, and in this case, that was our H2O. Our next question wants us to define electronegativity, which we've done already, so I'm going to skip that. Then it says calculate the difference in electronegativity between carbon and oxygen in CO2, which I've done, hydrogen and oxygen in H2O, which I've done. As we can see, both of these are greater than 0 and less than 2.1, which means that it indicates a polar covalent bond. The next question is more interesting to me. It's worth 6 marks. It says explain the difference in polarity between CO2 and H2O. Okay, so in other words, the polarity of the molecules. So is CO2 a polar molecule, a non-polar molecule? Is H2O polar molecule or non-polar molecule? And it says this is what they want us to refer to in our answer. Polarity of bonds, which we just calculated, by the way, and the shape of the molecules. So your answer will look as follows. So first of all, the bonds in both molecules are polar due to the difference in electronegativities, and we calculated this in the previous question. They want us to refer to polarity of bonds, so that's exactly what we do. Then they want us to talk about shape of the molecules. So I said the shape of the molecule over here is bent or angular. Either word is accepted. As we can see, it has a bent or angular shape. The reason why is because of these lone pairs over here, that lone pair, that lone pair. And the molecule, because of that, is polar, because it is a asymmetrical charge distribution. So that's one other thing that I would add in here. So this is an asymmetrical charge distribution, which I included for the last one, asymmetrical charge distribution. And it basically, what that means is that the one side of the molecule is more positive, the other side is more negative. And then the CO2 molecule, as you can see, has a linear shape. Therefore, it's non-polar because of the symmetrical charge distribution. 6 marks, it's quite a lot of marks. You do have to do quite a bit of writing, but I mean, it's worth the marks. If you want to see more videos like this, let me know. I can do more questions for you. Let me know what else you want to see, what else you're struggling with. Just let me know. Just comment down below, pop me a message, whatever it is. I hope to see you in the next video. Bye everyone.